The Smirnov transform, sometimes also known as inverse transform sampling or the inverse transformation method, is a way of generating random samples from a probability distribution on the real numbers. So if you have some random variable, some real valued random variable, and you want to generate random samples from that random variable, then in some cases the Smirnov transformation is the method of choice to use. And the basic idea, sort of simplistically speaking, is that it works by inverting the cumulative distribution function of that random variable. And now in some cases the CDF is not actually invertible, so there is actually a generalization that allows you to sort of think about a generalized sort of inverse of the CDF, and the Smirnov transform is still applicable in that more general case. So let's get the intuition here about what this is doing first, just to get the general idea of what's happening. Let's say we have some random variable. Let's say it's a Gaussian normal 0, 1, just a standard normal random variable. And so the CDF of this is going to look something like this. It, sort of starts out near 0, and then it climbs, and then it levels off at 1. So this will be 1 here, and this is the CDF of this random variable. So what is the CDF doing? Well, it's a map from the real numbers x to this interval, to the interval from 0 to 1, and in fact it's to the open interval. F never takes the value actually strictly 0, or exactly 0 or exactly 1. And so what happens here is we get some number. Let's say we get x, say here. Then f maps that to this number in the interval from 0 to 1. So I don't know, maybe that's 0.2 or something. Let's call that number a. So what the Smirnov transform does is it says, okay, draw a uniform sample from this interval 0 to 1. So now we get a random a, and then go backwards. So if this was the random choice that we got, we would look here, and then we would take the inverse, f inverse of a, and that would just be x here. So this would be f inverse of a. So that's the basic idea behind the Smirnov transform. Let's make this a little more formal. First, we'll consider a special case in which the CDF is actually invertible. So this is the invertible case. Invertible, if I can spell, the invertible case. And in this case, we'll say, let f be a CDF. And actually, let's make it, so for this case, we want it to be to the open interval from 0 to 1. And it's going to be an invertible CDF. So invertible meaning here, i.e., that there exists some function f inverse from this open interval 0, 1 to the real numbers, such that f inverse of f of x equals x for any real x, and also f inverse of a equals a for any number a in the interval from 0 to 1. So that's what this means, of course. Then, well, let's say this. If u is a uniform, let's make that all clear, uniform random variable on the interval from 0 to 1, then f inverse of u is distributed according to the CDF f. In other words, this random variable, f inverse of u, has CDF f. The CDF of this random variable is f. Now, sometimes I've seen in a couple cases both this theorem and the next one that we're going to talk about, the more general case, presented in a not very rigorous way, and the proofs were not actually correct. So I'm going to be very careful in giving the proofs of these results and really give all the details just so that everything is perfectly clear. One of the things which is a little bit strange is that sometimes people, and I think this causes some confusion sometimes, is that sometimes people define f inverse, even when f is not invertible, to be the sort of generalized inverse, and that can be confusing sometimes. But here it is actually the inverse, at least in this case. Okay, so here's the proof. We're gonna go step by step here. So let's say x and y are real numbers, and a and b are in this interval from 0 to 1. So the first thing, so we'll have some simple observations here. If x is less or equal to y, then f of x is less or equal to f of y. And that's just because f is a CDF, and so it's non-decreasing. So that's simple. Next, if x is strictly less than y, then f of x is also strictly less than f of y. And that's because, well, by this we know that it's f of x is less or equal to f of y, and f is, by assumption, invertible. So it must be a one-to-one function. It can't take the same value, so x and y are different, so f of x cannot be equal to f of y. And so it must be strictly less than. Third, if a, so remember x and y were in R, a and b are between 0 and 1. If a is less or equal to b, then f inverse of a is less or equal to f inverse of b. So in other words, here this was that f was non-decreasing, and now we're showing that f inverse is also non-decreasing. And this is because if, so let's write it over here. If f, so let's put it up here maybe. This is because otherwise, if f inverse of a were strictly greater than f inverse of b, then we could apply this property here. We could take f of both sides. Then we could take f of both sides, and we would have f of f inverse of a greater than f of f inverse of b, and this is b, and this is a, so a would be greater than b, and that contradicts our assumption. So we have this, and this holds just by the assumption, of course, just the definition of an inverse. So we have this, and now finally we lead up to the key property that we will need. This was all sort of just building up to the key property, which is that f inverse of a is less or equal to x if and only if a is less or equal to f of x. So if we start out over here, we can prove this direction, by taking f of both sides, and so f of the left side is a, so a is less or equal to f of x. We apply this property. And to go the other direction, we apply that f inverse is non-decreasing. So we take f inverse of both sides, and we get that f inverse of a is less or equal to f inverse of f of x, which is just x. Okay, so that's the key thing. And now recall that the CDF of a uniform random variable, so u is uniform, so the CDF of u let's call it h of x. This is 0, so the CDF of u is 0 if x is less or equal to 0, x if x is between 0 and 1 if x is greater than 1. Greater or equal to 1. Doesn't really matter at 0 and 1. So, you know, it's sort of going like this kind of thing. 0, and then it's just the identity on this interval from 0 to 1. Okay, and now we're ready to prove the result. So we want to show that f inverse of u has CDF f. So let's write down the definition of the CDF. So the definition of the CDF of f inverse of u is that it's the probability that f inverse of u is less or equal to some number x. So this equals the CDF of u of f inverse of u evaluated at the point x. And this is, so we can apply this property here, the purple property. F inverse of u is less or equal to x if and only if a is less or equal to, if and only if u is less or equal to f of x. So this equals the probability that u is less or equal to f of x. And this is the definition of the CDF of u. And we know that the CD evaluated at f of x. And we know that the CDF of u is h of x. So this is h of f of x. And since f of x is always, you know, in fact, in this case, it's actually strictly between 0 and 1. That's not particularly important for this step, but it is. And so this is equal to f of x by the definition of h of x. And so therefore, f is in fact the CDF of this random variable f inverse of u, and that's what we wanted to prove. So this is the simple case when f actually is invertible. It's going to this open interval from 0 to 1, and it's actually invertible. But this doesn't catch all the really, you know, there's a lot of interesting cases that this does not capture. It captures the Gaussian, but in fact, this is not the preferred method for sampling from a Gaussian. But so some interesting cases that this doesn't capture is, for example, an exponentially distributed random variable. It's always 0, you know, it's 0 when x is less than 0, the CDF, and then it sort of jumps up like this. So an exponential random variable is a nice, you know, it's a very nice sort of, has a very nice PDF and very nice CDF, and yet this does not actually apply, strictly speaking. And a more severe example would be if it's a discrete random variable, you know, like a Bernoulli random variable, like it jumps at 0 and then it has another jump at 1, this kind of thing. So next we're going to take a look at a more general version of this Smirnov transform to handle these more general sort of interesting cases when f is not actually an invertible function. So maybe let me say one last thing about how you would actually apply this. I think it might be pretty clear, but to apply this, what you would do would be, if you were to implement an algorithm on the computer, you would draw some random numbers, u1, u2 up to un, say, and then you would just evaluate f inverse of u1 up to f inverse of un, and then these would be your random samples from the desired distribution. Okay, so next we'll talk about the generalized form of the Smirnov transform.